Hello students, today we are going to learn about different properties of complex numbers. Beforehand we have learned about what are complex numbers and how we can express different numbers as complex numbers or into complex numbers. So let us go and see some of the properties. At first we'll learn the first property. It is given that if a plus ib is equal to 0, then a is equal to 0 and b is equal to 0. So that means if any complex number is equal to 0, then the real numbers within the complex number are 0 separately. Okay, so that means if c plus id is equal to 0, then it can only be 0 when c and d both are 0. Okay, the proof is given here. You see, when a plus ib is equal to 0, we can put what? A is equal to minus ib, and putting that there we can see a square equal to I square b square. I square b square, what we are doing, we are squaring on both sides, and then we are having a square plus a square is equal to minus b square, and last part is a square plus b square equal to 0 on transposition. What does it mean? See, a square plus b square equal to 0. When it can be equal to 0? Here a and b both are real numbers, and we know the square of the real numbers are always positive, or real numbers are always positive, so their sum can only be equal to 0 if they separately each of them are 0. That means what? A and b both are equal to 0. This is the first property. Now let us see the second property. The second property is about equality of complex numbers. So what does it say? The two complex numbers are equal if and only if the real and imaginary parts of one is equal to the real and imaginary parts of the other. So what does it mean? See, if z equal to a plus ib is one complex number, the other complex number b c plus id, then the real parts, okay, then that means a is equal to c. Look at here, a is equal to c and b is equal to d. Conversely also we can say if the real and the imaginary parts of two complex numbers are equal, then the complex numbers are said to be equal. Here two complex numbers are said to be equal if their real parts and the imaginary parts are equal. Okay, so that means here if you see, the real part of z1 is what? A, and z2 is c, so a is equal to c. Okay, and the imaginary part, see, ib is imaginary part, but b alone is a real number. Here b, ib and id are equal. That means what? B is equal to d. Okay, they are proving it also. They are taking conversely, we can prove it. If z1, conversely, if z1 is, we are taking it that z1 and z2 are equal, and we will show that it is only possible when a is equal to c and b is equal to d. Okay, see, when z1 is, we have taken z1 equal to z2, z1 equal to z2. So z1 we know, z1 equal to z2 means what? A plus ib is equal to c plus id. When a plus ib equal to c plus id on transposition, what we are getting? See, we are getting a minus c. We are transposing c on other side, it will be minus c, and transposing id on other side, we have minus id. Taking I common, here a minus c. Now see, the sum, this part, we are adding the numbers, and the addition of two numbers are 0. From the first property we know addition of 2, or we can say it is a complex number. If you see, if we use the property, the first property, this is a complex number. A minus c plus I into b minus c is a complex number which is equal to 0. And when it can be 0? By property 1, when a minus c is equal to 0 and b minus d is equal to 0. This means a is equal to c and b is equal to d. The proof is done. Please make a note of this. Okay, we'll head on to the next property, the closure property. The closure property we know, we have learned before also, closure property of whole numbers, integers, okay, rational numbers. Okay, same way the addition, subtraction, multiplication and division. Okay, this is addition, subtraction, multiplication, and this is division. But this one, there will always be a condition that z2 cannot be equal to 0. We know we cannot divide it by any number by 0, so that condition you have to follow. Otherwise, if z2 is not equal to 0, then the addition, subtraction and multiplication, if you look at here, you will see the set of complex numbers satisfies the closure property under addition, subtraction, multiplication and also division. Okay, it should be non-zero complex number. That means it is closed under this property. So multiplication, addition, subtraction and division of complex numbers always gives us a complex number 2. Next, commutative property. This also we learned before, we know. Okay, that means if you are adding a plus ib and say ib plus a, commutative property, both are same. Like that, if you take two different complex numbers, okay, we are talking about different complex numbers here, z1 and z2. So if you are adding z1 plus z2 or z2 plus z1, both are same. For multiplication also it will hold, z1 into z2 is equal to z2 into z1. There will be questions given in the there are questions which are given in the exercise. You might be asked to prove it also, so you can prove it. Same in case of associative property. Please go through this all. Okay, then distributive property. Okay, this I'm not going to explain. Identity property, this I am going to explain. See, also it is the same. You know, if you are adding 0 to a complex number, we get the complex number itself. Okay, so 0 is called the additive identity, and we know 1 is called the multiplicative identity. Okay, why? Because on multiplication of 1 to a complex number, we get the complex number itself. So it is basically the same what you have learned before in case of other numbers. Here also we will have the additive inverse. Yes, additive inverse. So as usual, we know additive inverse of z is what? Minus z. So if it is z equal to a plus I b, then its additive inverse will be minus z equal to minus a plus I b. Okay, so on addition of the additive inverse, we know we always get 0. So it will, so thus what we can say, every complex number has its additive inverse. Okay, and also same multiplicative identity. You know, we have multiplicative identity, so we have multiplicative inverse also. But remember, the multiplicative inverse is written this way, and the multiplicative inverse is also the reciprocal. The reciprocal and multiplicative inverse both are same. Like say one thing you have to see, this z is equal z inverse. That means z, don't say z to the power minus 1, it is z inverse. So z inverse is equal to 1 by z. That means, see, if say z is equal to a plus ib is the complex number. Okay, I will give you another example. Say the complex number zb 3 plus say 4i, then this z inverse will be 1 by z. Actually 1 by z means what? 3 plus 1 by 3 plus 4i. Okay, and as we have done rationalization in case of whenever we have square roots we rationalize. Okay, the irrational numbers we rationalize when it is in the denominator. Okay, we have to rationalize the denominator. Same way we have to, here will not say rationalize actually, here we have to remove the imaginary number. We cannot have imaginary numbers, or imaginary numbers in the denominator. Okay, we don't leave any imaginary number in the denominator, so that is why we multiply the denominator by its conjugate and make it real number. Okay, it is same like the rationalization we have done in class 9. Okay, rationalizing the denominator, and that was done in case of the irrational numbers. Here we'll do it for the complex numbers, that means the imaginary numbers, not complex numbers and or imaginary numbers. Okay, only for imaginary numbers. When we have a real number, that's not a problem, but complex number, here we can say complex number. Okay, and these things means it will hold all the algebraic identities. That means square. Okay, then we have cubes, and that one, that a square minus b square is a plus b into a minus b, that also it will hold. Okay, it will hold here. So for algebras what we have done, those properties or identities will hold. Now this one is important, conjugate of a complex number. Okay, remember, if z is the complex number, say a plus ib, then the conjugate will write as what? Z bar. Okay, it is given here, you see. Suppose z equal to x plus iy is a complex number and I equal to root over minus 1, this is there, then the conjugate of this complex number will be x minus iy. So they are said to be conjugate of each other. Remember, it is not additive inverse here. So say x plus iy is the complex number. Okay, its conjugate, that means z equal to x plus iy, its conjugate will be x minus iy. Now what we are doing here, you see what we are doing here, we are changing the sign in front of the imaginary part. Okay, we have to change the sign in front of the imaginary part. Remember, not the entire complex number. If you change the entire complex number, the sign of the entire complex number, it will become additive inverse, but it is not additive inverse, it is the conjugate. Why conjugate? Because while rationalizing, we know when we multiply two, that means like conjugate, we can say multiply, we will get a real number actually. That is why we use the term conjugate here. So that means we know why it is conjugate. That means if you multiply this x plus iy, write it again, if you multiply this x plus iy with this x minus iy, you know that it will be what? X square plus y square. It will become totally a real number. That is why we need the conjugates. Okay, we'll do some exercise questions, then we'll know the use of these conjugates. Some properties of real this conjugate complex number. Okay, when z is a real number, the conjugate of any real number is always the same. That is what it is said. And z is equal to 5, z bar is also equal to 5. I told you there will be change in the imaginary part only. When z is equal to 0, z bar is also equal to 0. When it is a pure imaginary number, then this z bar is equal to the additive inverse of z. So because what it is happening, if it is a pure imaginary number, what are pure imaginary numbers? If we give an example, say 3i. Okay, 3i, and we know the conjugate of 3i is what? We just have to change the sign in front of the imaginary number. It is minus 3i, and also we know the additive inverse is what? Again minus 3i. Additive inverse of z is again minus 3i. So from here what we can conclude? That z bar and minus z, that means the additive inverse of z, both are same when z is a pure imaginary number, remember. Okay, then we have the conjugate of a conjugate of a complex number is the number itself. So that means if you are taking conjugate and again its conjugate, then we'll get the number itself. Obviously the conjugate of x plus iy is x minus iy. See, look at here. The conjugate of x plus iy is what? X minus iy. Again if you take the conjugate, that means if you take the conjugate means bar, again it will become what? X plus iy. The conjugate of x plus iy is x minus iy. Again the conjugate of x minus iy is what? Again x plus iy itself. So that means what? The conjugate of a complex number is the complex number itself. Okay, this is what it says. The proof is given here. Then the sum of a complex number with its conjugate is always a real number. Of course, you know a plus ib. Here it is given here. The proof is given here. A plus ib and its conjugate will be a minus ib. You know, when we are adding this to this part and this part will be cancelled. Yes, because if when you are adding, we can cancel both the imaginary part, because one will be positive, the other will be negative. We will get what? Twice a, that means what? Which is real. Okay, that means the addition of two conjugates is always a real number. And the subtraction, you know, when it will be subtraction, when we will subtract two, that means the conjugate numbers, then we know the imaginary part will become positive and the real part will become negative. So we'll have only the remaining part will be what? You see this one. So a and a will cancel each other. This a and this a will cancel each other. What will be left is what? 2ib. That means what? We'll get only the imaginary number. So the addition of the conjugates, we always get a real number. Okay, and the subtraction of the conjugates, we always get an imaginary number. Okay, then again the product of conjugates, I already told you, we get a real number, a square plus b square. I have given an example. Okay, this one you have to remember. This one is important. The modulus of a complex number. This one you have to remember. This is one of the most important part in complex number. The mode of z is always a square plus b square. That means here z is the complex number, a plus ib. When z is the complex number, a plus ib, modulus of z is what? Modulus of z is root over of a square plus b square, and the value of a and b we can get from here. We'll get from here the value of a and b. Yes or no? Okay, and when you square on both the sides, we'll have a square plus b square. So this one you have to do. Modulus of z is what? Is root over of a square plus b square. When z is equal to x plus iy, then what will happen? When z is equal to x plus iy. When z is equal to x plus iy, then modulus of z will be what? Root over of x square plus y square. For a plus ib, it will be a square plus b square. For x plus iy, we have root over of x square plus y square. This, you might be given some complex numbers and you need to prove it. This all. You might be given some complex number, we may be asked to prove it. So it is given in the exercise, we'll do it. Okay. So I'll just tell you what is first one. That means the conjugate of the sum of the conjugate of the sum of two complex numbers is equal to the individual, the sum of their individual conjugates. Okay, and it is same in case of subtraction also, for multiplication also same, and for division also same. So the addition, subtraction, multiplication, division, when you find their conjugates, they are equal to the individual conjugates, and the operation remains the same. If it is addition, it will be addition. If it is subtraction, remains subtraction. Multiplication, for multiplication, it will remain multiplied to each other, and for division, they will divide. One will divide the other, so it will remain the same. Okay, we'll do it. This will be given as questions. We will prove it. Okay.